Welcome to the lesson on predicates and quantifiers. Let's look at the learning outcomes of this lesson. So by the end of this lesson, you should be able to use algebra of propositions to solve some algebraic propositions and describe and use the duality principle and replacement rule. Express the meaning of wide range of statements in mathematics using predicate logic, and apply universal quantifiers for the proposition, and apply existential quantifiers for the proposition. So during the past few lessons, we have been discussing a lot about propositions. So now this is an extension of that discussion on propositions. Let's first look at the algebra of propositions. So they're helpful in applications in real-world problem solving by drawing logical conclusions. So usually we need to convert a given description into propositional logic and simplify. So we need some rules for the process of simplification. So that's when the algebra of propositions come in. So we get introduced to some of the laws in this theorem. Let P and Q be any two propositions, and then the following laws will hold. Beginning with idempotent laws, P disjunction P is equivalent to P, and also P conjunction P is equivalent to P. That is idempotent law. Number two is associative laws. You can see the associative behavior of the two propositions P and Q related to conjunction and disjunction. And also third is the commutative laws, also regarding the commutative fashion of conjunction and disjunction. And then, of course, the distributive laws, also regarding the conjunction and disjunction of these two propositions, P and Q. Also, we need to identify the identify laws, domination laws, complement laws, double negation law, absorption law, contrapositive law, and De Morgan's laws. So here T and F are restricted to the truth values true and false respectively. So you can go through these laws. That should be straightforward to look into these laws to understand what each of the law is trying to tell us. So these laws have been set in place so that when we are presented with proposition logic, so that we can simplify statements relating to propositional relationships. So let's take an example so that we can identify the application of these different laws. So in this example, we are required to prove the following statements by developing a series of logical equivalences. So part A is negation of P disjunction, negation of P conjunction Q is equivalent to negation of P conjunction negation of Q. So let's first look at part A, trying to prove that statement. So what law is, so we need to take it step by step and apply different laws at different steps. So the first step would be to apply De Morgan's law for the statement, for the statement given in the left hand side of the statement. So applying De Morgan's law, you will get negation of P, conjunction, negation of P, conjunction Q. And also in the second step, you can apply the De Morgan's law. Third step, the double negation law. Fourth step, by the distributive law. Fifth step, by the complement law. Sixth step, apply the commutative law. And finally, apply the identity law to arrive at the final answer, which is negation of P, conjunction, negation of Q. So we can prove that these two statements are equivalent. So how did we arrive at the conclusion? By applying a series of algebraic laws. Similarly, statement B, we need to prove P disjunction Q is equivalent to negation of negation P, conjunction negation Q. So we start with the left-hand side as usual. So in this case, we start with the right-hand side, which is negation of negation P, conjunction negation Q. At the first step, we apply De Morgan's law to simplify. And the second step, by applying double negation law. So by applying two of the laws, we arrive at the final answer, which is P disjunction Q. So that is an example. Those two are examples of applications of these laws to simplify propositional logic. Now we get introduced to the concept of the dual. So for any given compound proposition P, we can obtain the dual of that proposition by replacing conjunction with disjunction and disjunction with conjunction and T by F and F by T. So what we do is we do a simple replacement. So for example, dual of P conjunction Q, disjunction negation P is P disjunction Q, conjunction negation of. And next one is the duality principle. So if two propositions are logically equivalent, then their duals are also logically equivalent. So that is the duality principle. And next is the replacement rule. So for logically equivalent propositions P1 and P2, so that P1 is equivalent to P2. Assuming there is a compound proposition Q in which P1 appears, the replacement rule says that we may replace P1 by P2 and then the resulting proposition is logically equivalent to Q. So basically replacing, in this case, P1 by P2, the resultant proposition is logically equivalent to the original proposition, which was Q. So that is the replacement rule. Take an example on this. Given the conditional proposition P implies Q, we define the converse of P implies Q as Q implies P, the other way around. The inverse of P implies Q as negation of P implies negation of Q. So converse versus inverse. And the contrapositive of P implies Q as negation of Q implies negation of P. So once again, we go to the truth table to explore the truth values for each of the statements. So for all the combinations of truth values for P and Q, we examine P implies Q, Q implies P. Negation of P implies negation of Q, and negation of Q implies negation of P. So we see that from the truth values and the truth table, conditional proposition P implies Q and its contrapositive, which is negation of Q implies negation of P, are logically equivalent. So how did we observe that? From the truth table, because all the truth values for those two conditional propositions are the same. That is in column 3 and column 6. You see that all the truth values are the same, and therefore we can conclude that those two conditional propositions are logically equivalent. Right. So with that, we move on to the predicate logic. Let's try to understand what the predicate means. So formalization of the mathematical concept of a statement. So we try to define a statement formally in a mathematical perspective. So the predicate usually does not have a definite truth value. So the truth value of the predicate will depend on an unknown variable. Example, we have a predicate x greater than 3. So we cannot define a truth value for this statement or the predicate because we do not know the value of x, because it's an unknown variable. Depending on the value of x, this predicate can be true or false. Right now, as the definition, the predicate does not have a truth value. And then to define the propositional function, denote x greater than 3 by px. So we now have a notation for that, which is px. So px is the value of the propositional function p at x. So once the value has been assigned to the variable x, the statement px becomes a proposition. So predicate becomes a proposition and has a truth value. So for all the values of x, px will have a truth value. Only when there is an assigned value for the px, we will have a truth value for this proposition, which is in this case px. So moving on with further information about predicates, start by formally defining a predicate. Let px be a statement involving the variable x, and let d be a set. We call p a propositional function or predicate with respect to d if for each x in d, px is a proposition. All right. So we call d the domain of discourse. We'll take an example to understand it better. Part A, let px denote a predicate x greater than 5. Then p1 denotes the proposition 1 greater than 5, which is false, and the truth value becomes f. While p10 denotes the proposition 10 greater than 5 with truth value true, because the statement becomes true in that scenario. Next example, let qxy denote x squared plus y squared equal to 1. Then we can have different values for x and y, in which case q01 denotes the proposition 0 squared plus 1 squared is equal to 1. We understand that statement becomes true and the truth value becomes p. While q11 denotes the proposition 1 squared plus 1 squared is equal to 1. In this case, we know that the statement becomes false with truth value f. Now we will move on for more examples with the compound predicates. Example 8.4, part A, let Px denote x squared get greater than 10 and Qx denote x is positive. So in this case, for example, Px conjunction Qx denotes the predicate x squared greater than 10 and x is positive. So we have a combination in this case, or compound predicate. So example B, let Qxy denote x is equal to 2y squared. Then negation of Qxy denotes x is not equal to 2y squared. So those are examples for compound predicates. More on compound predicates in example 8.5. Let Pxy denote x greater than y and let Qx denote x less than 2. So we are asked to find the truth value of the predicate negation of Pxy conjunction Qx when x is equal to 3 and y is equal to 1. So we are given the values for x and y. So how do we approach the solution? We need to find the truth value of the statement negation P31 conjunction Q3. So we find that the truth value of P31 is true and Q3 is false. Therefore, the truth value of P31 conjunction Q3 is also false, because true and false becomes false in the conjunction operation. Hence, the truth value of negation of P31 conjunction Q3 is T. It becomes T because the original truth value was. Now we move on to introduce quantifiers. Quantifiers help us handling for all and for some in mathematical statements. So let's first look at what we mean by a universal quantifier. Let P be a propositional function with domain of discourse D. And if we say for all x, Px, this denotes a universally quantified statement. And you have the symbol for this, that means for all. And this is called the universal quantifier. For example, for all x, Px is denoted by the notation for the universal quantifier. So the statement for all x Px is true if Px is true for every x in the domain of discourse D. And also the statement for all x Px is false if Px is false for at least one x in D. So any of the values, for any of the values of x, if Px is false, and for all x Px will be false. So this is the behavior of the universal quantifier. So let's take some examples to understand this better. Consider the universally quantified statement for all x, x squared is greater than or equal to 0. So in this case, we take the domain of discourse to be R, which is real numbers. The statement becomes true because for all the real numbers, for every real number x, it is true that the square of x is positive or 0. So this becomes true. Take another example, 8.7. Determine whether the universally quantified statement for all x, x squared minus 1 greater than 0 is true or false. Once again, the domain of discourse is R, real numbers. So in this case, we note that the statement is false since, for example, if x is 1, the proposition 1 squared minus 1 greater than 0 is false. So we find one value, in this case, a sample value, which is x is equal to 1, where the proposition becomes false. The value 1 is a counter example. We call it a counter example to the statement for all x, x squared minus 1 greater than 0 is false. Although there are values of x that makes the propositional function true, the counter example provided shows that the universally quantified statement is false, because at least for one value, we find that the proposition becomes false. So because of that, the statement becomes false, because there is at least one value of x in which the statement becomes false. And then move on to the existential quantifier. Let P be a propositional function with domain of discourse D. Then we can say there exists x, Px. So in this case, this is called an existentially quantified statement. The symbol is given an inverted E letter. It means there exists. And it's called an existential quantifier. The statement there exists x, Px is true if Px is true for at least one x value in D. The statement there exists x, Px will become false if Px is false for every x in D. It has to be false for every x in the domain of discourse for the statement to be false. If there is at least one value which is true, then the statement is true, because the existential quantifier says there exists. So if there's at least one value, the statement will be true. Going for examples, consider the existentially quantified statement. There exists x such that x over x squared plus 1 is equal to 2 over 5. So here the domain of discourse is R. Once again, the real numbers. The statement is true because it is possible to find at least one real number within the domain of discourse, x, for which the proposition x over x squared plus 1 is equal to 2 over 5 is true. For example, if you put x is equal to 2, you obtain the true proposition where 2 over 2 squared plus 1, which is equal to 2 over 5. It is not the case that every value of x results in a true proposition. For example, if x is equal to 1, the proposition 1 over 1 squared plus 1 is not equal to 2 over 5, in which case the proposition becomes false. But we can find at least one value for x where the proposition becomes. We now move on to a special remark about the quantifiers. Take the statement for all x, there exists y, Px, is not the same as there exists y for all x, Px. So let's understand this using an example. Considering the statements for all x, there exists y such that x is less than y. Part B is there exists y for all x such that x is less than y. So for this example also, the domain of discourse is R, real numbers. Statement A is true, but statement B is false. Let's try to see why, noting that statement A states that whatever number x we choose, we can find a number y such that x is such that x is less than y. For example, y equal to x plus 1. So that's statement A, which holds true. But take the statement B, which states that there's number y which is simultaneously greater than every number x. But however, we should understand that this is impossible, because if x is equal to y, this relationship does not hold. X less than y does not hold. So we can find at least one example where this will not hold. Therefore, the overall statement becomes false. And that gives us the indication that the above two statements, A and B, they are not the same, or they are not equivalent. So they mean different things, and they can have different truth values. With that, we reach the end of this lesson about predicates and quantifiers. In the next lesson, we will discuss about relations. Thank you.